we're going to do integration of rational functions. And a lot of today, if not all of it today, is going to be preparation to do that. So we're just going to do all the various kind of skill things that we need to be able to integrate a rational function. So let's start by telling you what a rational function is. This is an example of a rational function. It's basically a fraction function. So we're going to learn techniques for integration of fractional rational functions. And they're going to fall into two categories. The first type of rational function, and this is an example of it, are ones that you can solve by doing u-subs. And we're not really, for completeness sake, I'm showing you this, but for the most part, we're not going to do questions like that. But this is a u-sub. Can you tell me what the u-sub would be that you would use to solve this question?
X squared plus 1.
Agreed. Pretty straightforward. Won't it typically be the bottom of the fraction? You know, if it's a fraction, the guy in the bottom is typically your u-sub. And the second type are going to be the ones that u-subs do not work for. So here would be an example. Can you just trust me that there's not a u-sub in the world that will save you? Right? The only real u-sub is that bottom term, and can you trust me it doesn't work? You're going to get a guy left over. So, well, that makes the world nice and simple. Rational functions, at least the ones we're going to deal with in 7.4, fall into two categories. There's the ones that you can use a u-sub on and the ones that you can't. And we're going to really focus most of our time, almost all of our time, on these situations, because we know how to do u-subs, right? We've done that in another section. There's no point in doing lots of these because we kind of know how to do them. But we don't know how to do the ones that u-subs don't work for, right? Like this. So far, so good. So let's look at these ones. They're going to end up being two distinct methods for solving them. One of them is called the cover-up method. And the second method is called the general algebraic method. Have any of you heard of either of those two terms, maybe at school, or maybe if you've done, hopefully if you've done Calc 2 before? Have you heard of either or any of those two methods? Okay, so this is going to be new stuff for you, for most of you. And we're going to look at today this cover-up method. Tomorrow we'll look at this one probably, but this one today. Okay. Now, before we even get to how to do this, fella, let's kind of take a step back and look at integrals we know the answer to. If I asked you to integrate 4 over x plus 3, I hope you're all saying, yeah, it's basically just 4 times the natural log of x plus 3. I'd say. Are you comfortable with that? You all seen that kind of thing? Isn't 1 over x just the natural log of x? So be aware that WebAssign, because WebAssign is awkward, don't they sometimes stick an absolute value around this and sometimes they don't? So when you're putting your answers in, I know, maybe the safest bet is just always give it an absolute value and keep it happy, right? And just in case it's causing trouble. Now, if this was negative 1/2 over x minus 1, it would be negative 1/2 the log of x minus 1. We're all happy with that. The thing on the top can be anything, even an ugly fraction like negative a half. However, you got to be careful when the denominator isn't an x plus or minus a number, but a multiple of x, right? 2x plus a number, 4x plus a number, right? Minus 2x minus a number, that kind of thing. It's not that. There's a bit missing. It is going to have a 4 log of 2x plus 3, but what does that 2 next to the x do? How do you cope with that or incorporate it?
When you have to divide the whole thing by 2?
Yeah. It's called the linear shortcut method, right? So the correct answer is 2 natural log of 2x plus 3. So if you have 5, 3x minus 1s, for instance, you get 5, the natural log of 3x minus 1, and that 3 you divide by. Are you happy about it now? That 3 generates this 3. If you do not like this shortcut, right, the linear shortcut method, couldn't you do a little baby u sub of 3x minus 1 and then 4 lines later get that? I mean, if you need to be convinced, that would be it. Are we comfortable now about finding the integrals of numbers over some linear combination of x's? We're comfortable with these guys? Right, so let's move on and look at some style point issues. Let's suppose I do an integral and it ends up being that, right? So that's my answer. We can call that guy that. Would you agree? 2 times a log is the same as a log of something squared. Can you remember that rule? Okay. Suppose we get an answer that looks like this. And suppose we do some integrals and the answer ends up being 2 logs being added in this case. And we would like to combine them into a single log. So style points involve us taking the expression and you're trying to make it in some sense simpler. So I've got a log here and I've got a log here. What do you get if you add 2 logs? You get a single log made up of what?
The contents multiplied.
Agreed. These are called the, whoops, bucket. These are called the laws of logs. So the first law of log says a multiple of a log becomes a power, right? So 3 log a becomes a log a cubed. This log of a plus the log of b becomes the natural log of ab. And the log of a, take away the log of b, becomes the natural log of a over b. Are we all comfortable? Can you remember? God, where would that be? The end in Math 141? Properties of logs. So if you have 2 logs added, combine them into a single log by multiplying the 2 individual pieces. If you have a log that's a multiple of somebody, turn it into a power. And for completeness sake, you could have 2 logs being subtracted. Right, when you have 2 logs being subtracted, what do you think you now do if you want to combine them into a single log?
Divide them.
And first one goes on top, divided by the guy you're subtracting on the bottom. Are you comfortable with that? Right, so I'm going to put the whole package together. You might get 3 times the natural log of 2x plus 5. Take away 2 times the natural log of x minus 1. Now, if you want to make that into a single log, you probably would do it in 2 goes. If you're really good, you could do it in 1 go. Won't the 3 log get you a log of something cubed? And the 2 log gives you the log of a guy squared. Would that seem reasonable for the first step? Taking the multiple 3 and calling it a cube, and the other multiple 2 and calling it a square, and then 2 guys subtracted. Okay, so for style point purposes, you're going to deal with a lot of integrals, and many of them end up being logs. And so you want to be comfortable about how to make them look pretty, right? How to take a whole load of logs that are added and subtracted or multiplied and just stick them in one big log. Are we cool with that? You comfortable with that process? As you say, there's nothing integrating going on right now. We're just doing skill building. Okay, I just thought of one. I guess I should put it in. If the multiple on the outside of the log is not a number like 2 or 3, which gives you squares and cubes, but is a fraction like a half, for instance. Technically speaking, you could start off by calling it that. Agreed, it's just a half power. But it would look nicer as a square root. But both of those are valid, and I don't see any problems with them. If you write that, I'm quite happy. If you do that, I'm even happier. Are we good? Right, the halves just give you square roots and thirds give you cube roots. Now it's time to look at this method called the cover-up method. So we are going to integrate that guy. And I'm telling you right now, as I said at the start, you can't use U subs. X subs don't work either, by the way, but I don't think you're even going to go there, right? That didn't even look like a starter. So what we're going to do is we're going to take this fraction and we're going to break it into smaller fractions. But before we do that, in some of the questions at least, you're going to have to factor it. So before you even try and do this method, either one of these, but in this case, cover up. So I should tell you what one we're doing right now. We're going to do the cover up method. Make sure it's factored, especially the bottom. Don't really mind if you don't factor the top, but definitely factor the bottom. And the trick is that we're going to take this single fraction and we're going to break it into 2 smaller fractions that look like that. And this A and this B are placeholders. They're going to be numbers when we're finished. It's going to be 7 or 3 or -2. It's more likely going to be 3/4 and 5/11 because you almost always get ugly fractions in these questions. So A and B are going to be numbers. And we're going to take this single fraction then and break it into 2 baby fractions. Do you notice that the baby fractions use one of each denominator? These fractions, both of them, are called partial fractions. One of my students from the other Calc 2 gave a really good, to me anyway, a really good way of thinking about this. what we're going to do here is we're going to deconstruct this fraction into its pieces. And I kind of like that term because it kind of makes sense in my brain, right? You're breaking it apart into what it was made from. Normally, don't we go two fractions and we mook them into one, right? We know how to go that direction. If I told you this was 3 and 2, couldn't you eventually make it go that way, right? What we've never done before is take a completed answer and break it apart, right? Deconstruct it. And this method is called the cover-up method. And I was telling my other students, so I'll tell you as well. I learned this method 50 years ago in Scotland, of course. And I remember seeing that method. And you're going to have the same experience if you've never seen it before. We're going to do 3 examples, at least 3. And the first time I show you this method, it's going to look like magic. And you're going to think, what did he just do? And why did that work? And then the second time, hopefully it's going to be, why did that work? And then the third time I'm going to do it, you're going to say, I don't care why it works. It works, I'm going to use it. Right? So that's what my goal is. It's not called the cover-up method back in Scotland. It's called the finger method. But unfortunately, in America, that has the wrong connotation, so we don't use that term. But if you want to search for it, you could certainly do that, but you have to be careful how you search for it. You may get unsuitable references, right? So let's show you the magic. I got a little piece of paper. Where is my next piece of paper? Here it is. So what we're going to do is we're going to find out what number A and B is, right? What fraction this is and what fraction that becomes. So let's ignore that guy, so I'll cover him up. And let's go hunting for the number A. Now watch what I do. Put little brackets in there. I want this number A, so I cover up the x plus 1. You see there's a little fraction there, 2x plus 1 in the top, x plus 2 in the bottom. Do you see that guy? So that's the first part of this magic method. Then you use the number that makes x plus 1 0. What value of x makes x plus 1 0?
-1.
-1. If you plug in -1 in the top, you get 2 lots of -1 plus 1, which is -1. And if you plug -1 in the bottom, you get -1 plus 2 is 1. So you end up with -1 over x plus 1. Say it again, right? Cover up the x plus 1. Put -1 into everything that's left, the top and the bottom, and you got 1. Would you agree that's just magic? Right? Would you also agree you can't really write that down as a formula? Isn't that actually, it's helpful to use your finger to cover things up? Right, let's go for the other one. The x plus 2. Right, well, if you want the x plus 2, you cover up x plus 2. What value of x makes x plus 2 0?
-2.
Plug -2 in to what's left. -2 add 1 on the top gets you -4 add 1 gets you -3. -2 add 1 on the bottom gets you what? -1. That guy over that guy gets you plus 3 over x add 2. So according to this cover-up method, this fraction has now been reduced to its 2 partial fractions. Let's prove that this actually has worked. If this works, shouldn't I be able to combine them and they end up being this guy? Do you agree? If I add these 2 fractions together, it should equal this guy. Well, this might be a while since you've done this, but if you want to add 2 fractions like this, they have to share a common denominator. So I'm going to multiply this fraction by the special version of 1x add 2, and I'm going to multiply this fraction by the special version of 1 called x plus 1. And what do I get now? I get negative x take away 2 over this guy plus 3x plus 3 over this guy. You happy with that line? And since they both share the same common denominator, I can add the numerators, and negative x add 3 gets me 2x, and negative 2 add 3 gets me 1. Bingo, didn't it work? I am not going to do this check ever again. Will you just trust me that if you do the process right, it works? But just for one, let me show you how. Okay, next guy. Three x plus 6 over x minus 1, x plus 3. Okay. Now that's going to split as an a over x minus 1 plus a b over x plus 3. Are you happy about how you split the partial fractions? So that seemed pretty intuitive, the two pieces. Okay, let's get the first one. Right, the x minus 1 guy. Well, cover up x minus 1. What value of x then makes that 0? 1 makes it 0, right? Plug 1 into what's left. 3 times 1 plus 6 gets you 9. 1 plus 3 gets you 4. 9 quarters, which is much more common. You tend to get ugly fractions when you do these. You happy about covering it up and plugging in 1? Now let's do the other side, the x plus 3 side. Okay. Cover it up and put in negative 3 now. In the top, if you put in negative 3, you get negative 3. In the bottom, if you put in negative 3, you get negative 4. So that is going to be 9 quarters x minus 1. That's a positive, plus 3 quarters x add 3. Would you agree it's clearer what I'm doing, even if you don't know why it works? So we're going to do one more. And the next one, do you now not care why it works? You just know how to do it and it works, right? So, Alec, give me a number from 1 to 10.
7.
Okay. Plus or minus something more. Give me something to add or subtract. 1 to 10 again.
3.
Minus 3.
Take away 3. Okay. Right, so we're going really crazy with this one because basically we're picking random digits, agreed? So if it works for random digits, won't it work for every situation that looks like this? Okay, Matthew, give me a plus or minus number between 1 and 10.
Huh?
Yeah, give me a number between 1 and 10, positive or negative. Can you see me? Yes.
Oh, okay. So someone else said something,
Oh.
so I was confused.
Oh, there
Um,
may be more than one Matthew. I didn't realize that.
-5 halves.
No, we're not doing 5 halves. You're getting 5.
Okay, fine.
Sabrina, then, why don't you finish off? Give me a number to complete this question.
7.
A 7? Minus or plus?
Minus.
Minus, okay. So would you agree this is probably going to give you the ugliest looking answer in the world? But if you can do this one, can't you do any of them as long as they look like this, right? So it's going to be an a over x take away 5 and a b over x take away 7. So let's cover that guy up. If you cover up that guy, what value of x will I use? I'm covering up the x minus 5. What value of x will I use on what's left?
5.
Okay, 7 5s are 35, take away 3, leaves me with 32 on the top. And 5 take away 7 on the bottom, leaves me negative 2 on the bottom. Would you look at that? It's actually quite a nice answer. Negative 16. Okay, let's go the other side. Okay, I'm going to cover up the x minus 7 now. Would you agree 7 is the number to use? Right, 7, x minus 7, 7 is the number to use. 49, take away 3 is 46. Oh, would you? You lot are really good at picking nice numbers. And that ends up being 23 over x minus 7. Now, if you're wondering, why are we even dealing with these partial fractions? Well, can you imagine you were going to integrate this thing? As it stands, would you agree you can't do it? There's not a U sub in the world or, you know, some clever algebra, apart from this algebra, to do it. But if you break it into its partial fractions, can't we integrate these guys? Isn't this guy just going to be negative 16, the natural log of x minus 5, and this guy's going to be 23, the natural log of x minus 7. So what we've done essentially is take an integral that we don't know how to do, break it into its partial fractions, and since these guys are the same as that guy, right, then integrating this is the answer to the integration of that. Isn't that quite a common technique in math? If you can't get the answer to a problem, turn it into something else that you can get the answer to, and use that answer to predict that one. Isn't that what U subs do? You can't integrate it the way it looks, so you use this algebra trick called U subs, and it turns into an integral that you can do, and then you work backwards to what you've got. Pretty cool. Now, there's one combination of this that we haven't done yet. But before we do that, I'm going to give you 2 to try yourself. So that's the first one. And that's the second one. Okay. So you have got 1 minute. Go for it. See if you can get at least one of them done in 1 minute. And I'll set up the partial fraction part for you. Last few things. Okay, here we go. Let's get this number here, the one that belongs with x minus 1. We cover up x minus 1 and plug 1 in. The top guy you get is 2 and the bottom guy is 3, so 2/3. Do we agree on that? Right, move over to this side. This time I'm going to put -2 in, right? So you plug it into the top, you get -7. You plug it into -2 into the bottom, you get -3. So our final answer is 2/3 x minus 1s plus 7/3 x plus 2. Does that look good? Yes? Okay, because you know I screw up. So x minus 2 guy. Cover it up, plug in 2. You get 8 take away 2 is 5 on the top. And 2 add 3, 5 in the bottom. So that's 1. It's a nice looking answer. And then you do the other fella. Now if you cover up x plus 3 and you put in -3, that's -15 on the top and -5 on the bottom. I am good at picking, by sheer coincidence, nice numbers. Did you get 1 and 3? Or at least agree with 1 and 3? So what have I not done yet? I guess the question is, it looks like I've done them all, but not quite. All I'm doing here is adding a multiple on the bottom. So instead of x plus 1 or x minus 7, it's now going to be 2x plus 1, 3x minus 7, right? That extra 2 is going to make a little difference, but only a tiny little difference. It's still going to split into its 2 partial fractions the way you would have expected. Okay, so nothing different here. Okay. I'm going to cover up the 2x plus 1. Exactly what you'd expect. The value of x that I use now is not -1. What value of x do I now use in this new situation?
-1/2.
Right. Do you notice it's the same thing? What value of x makes it 0? It's just a little bit different, right? It's a little bit easier. Not easier. It's a little bit more difficult to do. But -1/2, would you agree? So 3 lots of -1/2 add 2 leaves you with 1/2. On the bottom, -1/2 take away 4 leaves you with -9/2. Can you see how ugly the fraction is that you're probably going to get in these questions now? And we have to figure out what that simplifies down to. So we're going to take 1/2 on the top over a -9/2 on the bottom, and it's going to turn into a nice fraction, or a better looking fraction at least than it is right now. Does anybody know what that fraction is?
-1/9.
You want to tell us your thought process? You're correct.
Because when you're dividing fractions, you multiply the bottom. So then you have to flip the fraction. So then it'd be -2/9, and then multiply across, and then you get -2/18, and then simplify to 1/9.
Agreed. You all comfortable with that? That you're going to probably have ugly fraction divided by other ugly fraction, and this is what it would do in hand. Of course, if you're really stuck with fractions, 1/2 divided by that. Let's see what that looks like. I like putting brackets around fractions because you're never quite sure what the order of calculation is going to look like. So there's the top, 1/2 divided by a bracket, -9/2, close the brackets, and enter. And then hit the math button and choice 1. And there's your -1/9. You see how that worked? Right. Totally random. Can you imagine you got 4/11ths on the top and negative 7/5 in the bottom. Would you agree that would be a pretty ugly looking answer, right? Well, we could do it this way, and that's actually the best way to do it, but you could say top fraction 4/11, right? Divided by bottom fraction, negative 7/5. Hit the button, and then go math button, number 1, which should turn your answer into negative 20/77. You see, it gets you the answer all simplified down and good to go. You happy with that trick? Well, you probably knew it on how you can deal with fractions. So, returning to our question, this fella is now negative 1/9 over 2x plus 1. And for the purposes of what we're doing, that is okay. Normally, that would not be a good way to leave it, but we're going to leave it that way because it's going to lead to an integration later anyway, so there's no point in fixing it. Now, this fella. Well, cover this, get out the site, x minus 4, cover it up, and put 4 in. Well, 3 times 4 add 2 is 14, and 14 over 9. Oh, there we go. It's positive. Are we comfortable about how 3x add 2 and 2x minus 7s, and when the denominator is a little bit uglier, right? How we could do that. Right, let's do another one of that similar kind. So 5x plus 2 over 2x minus 1, 3x minus 2. It's probably close to the worst combinations you could get. There's our 2 partial fractions. Let's get this guy here. Cover up the 2x minus 1. Done. What value of x will I now use?
One half.
Okay. 5/2 plus 2 is 4.5, which is 9/2. So 9/2 go on the top. If you plug a half into the bottom, you get 3/2, take away 2, which leaves you with 1/2. And can you trust me that that ends up being 9? So I guess sometimes you can get lucky, right? Let's go for the other side. I don't know why this causes people problems, but it does. What value of x do you use in this situation here?
Two-thirds.
I think I heard it, 2/3. So cover it up. 5 lots of 2/3 plus 2. Sometimes you might just want to have a scratch bit of paper beside you, right? I know what that's the top's going to be. That's just 5x add 2, right? So it's going to be 10/3 plus 2. That's going to be 10/3 plus 6/3. And so 16/3. Okay, so the top is 16/3. And 2/3 on the bottom. 2 times 2/3. Take away 1. Is 4/3 take away 1. It's 4/3 take away 1 is 1/3. And oh God, I am really good today, because that ends up being 16. I have no idea how I got so lucky that both answers end up being really nice. You know that they're typically 17, 19ths and weird stuff. Okay, so for our last question for today, let's get you to try one. And so, Caitlin, we're going to blame you. So tell me who the numerator is going to be. Keep the numbers between, plus and minus 10. So how many x's?
6
Okay, plus or minus what?
plus 7.
Okay, And we need some factors in the bottom. Right, what do you want in the bottom? Remember, you're going to have to do this question as well, right?
Yeah. Let's do 2x minus 1.
Coward. Come on, one more.
And 3x plus 4.
Okay, guys, you got 2 minutes. Go for it. Coming up in the last few seconds now. Okay, let's get started. I'll go for the first one, the A. Right, so 2x minus 1 gets covered up, and you plug in a half. If you plug in a half here, you get 10 on the top. Right, 6 lots of half is 3, 3 on 7. And you put a half in the bottom, you get 5.5, which is called 9 halves. And eventually, according to what my brain is telling me, you get 20/9. Does that look good? Okay, now we're covering this guy up, and we're going for the really ugly one. That one. Now, if you cover that up, the x value you're going to use is -4/3. It's whatever makes this 0, and x is -4/3. Do that. So it's going to be 6 times -4/3, add 7 on the top, and 2 lots of -4/3, take away 1 on the bottom. Well, that guy and that guy gets you -8, and -8 adds 7, I believe, is -1. And that's -8/3, take away 3 more, so it's -11/3. And I believe that is positive 3/11. Do you agree with those two guys? Then we are finished for today. Say your last name and bye-bye.